Okay, so yeah, as I said last time, there is a gap between the theory and empirical observation for the generalization gap understanding of AdaBoost. So this lecture, we will focus on that. We will review some of the margin theory, margin functions, and we will talk about that. I'm looking at the chat right now. I think people are having questions about the homeworks. So I don't think we have time to talk about the homework right now. But yeah, I would rather have the discussion on Piazza. Cal has been telling me that we have some questions regarding the homeworks. So, I plan to look at it again later after the lecture. Is that okay? Okay, wonderful. So let's continue. I really hope we can finish talking about AdaBoost today. So we can, hopefully we'll also have a little bit of time talking about the generalization of neural nets. And then we can really focusing on applying these classical learning theory to modern machine learning deep neural nets. Okay. Right. So last time, I think people have confusions about this Rademacher complexity of convex halls. And essentially, I think, just to review it again, we define the convex hall of the hypothesis class H as the linear combination of the hypotheses within that hypothesis class, but the coefficients have to be greater than equal to 0, and the summation has to be smaller than equal to 1. So the lemma is, very interestingly, you can see the empirical Rademacher complexity of a hypothesis class H is equivalent to the empirical Rademacher complexity of the convex hull of the hypothesis class H. Okay, so the proof really is very simple, right? I mean, it really involves, let me take out my marker. It really involves the definition of the convex hull, and of course involves the definition of the empirical Rademacher complexity. And then, essentially you will see is an exchange of summations, putting something outside and putting something inside. It doesn't change the result, the overall result. And then the most important thing is this part. This is basically saying that if you wanted to find a supermon of a linear combination of a bunch of things, then you are essentially putting the weight, the coefficient on the one that has the maximal value. So essentially it becomes the maximum of this quantity over all the vertices of this convex hull. Okay, so maximizing vector mu for the convex combination of p items is the one placing the weight on the largest item of the sum. Okay. Now, what really happens is, if you look at this, then you are saying I'm doing a supermon over hk in H, and then also taking maximum of k within this, vertices hk. But if you think about it, this is really saying I'm just trying to take the maximum, the hypothesis from H that is achieving this supermon, right? So that's equivalent to this equation here. And notice that this is hk and this is also hk. Okay? Well, so you can imagine now I don't have to put it as hk, I can just put it as h in H, and here also h of xi, right? So if you recall the definition of the empirical Rademacher complexity, this is nothing but an empirical Rademacher complexity of H. Okay, So this completes the proof. Basically, the most important thing is maximizing vector mu for the convex combination of p terms is the one placing the weight on the largest term of the sum. Okay. I hope there's no more questions. Now let's move on to the margins. We need to review some of the margin, the definition of the margin, the geometric interpretation of margin in order to understand why AdaBoost is resistant to overfitting. Okay. Also, one thing I really want to emphasize is that AdaBoost is really powerful only because you have made this weak learning assumption. You are assuming that all the base learners kind of satisfy this weak learning condition. We'll see that is actually not, seems like a very simple thing, but if you think about it, it's not very, it's a rather strong condition, although it's called weak learning condition. I'll talk about that later when I finish talking about this, generalization ability analysis of AdaBoost, but keep that in mind. Because there's no free lunch, that's what they said. I truly believe in that. It seems like AdaBoost is too good to be true, but just keep that in mind that we do have a weak learning condition we have to satisfy. And this weak learning condition actually is a kind of distribution agnostic. I'll talk about that, okay? So margin review, I wanted to first review the L1 margin. We're going to denote it as rho sub 1x, and I usually just say rho 1x for simplicity. So L1 margin rho 1x was labeled space -1 + 1 for a linear combination of base classifiers. So this G of x is a linear combination of the base classifiers HT of x. T is the index of the base classifiers, and you have capital T such ones. So if you consider this is nothing but an inner product, right? So you can write it as a vector form of this coefficient alpha t, putting that coefficient alpha t into a vector alpha, and then putting the base classifiers into a vector of hx. Then it becomes the inner product between the coefficient vector and the base classifier vector. Okay, with elements, of course, elements of the alpha have to be greater than equal to 0. That's the definition. So then the rho 1x is just defined as y. So what is y? Y is the corresponding ground truth label associated with x. So rho 1 of x is just y multiplied with this inner product. So this inner product essentially is the strong classifiers, the linear combination of the base classifier. But very importantly, you have a normalization term. You're normalizing the L1 norm of the alpha. So essentially the summation of all the coefficients. Okay? So this is very important. Also, you notice that this margin definition, you have to do it when you can only define it when you have y. If you don't have the y, you don't know how to define it, right? You have to know the ground truth y. So also, another thing I wanted to emphasize is this L1 margin rho 1x is with respect to a specific data point, x and y. Okay, so it is for a specific x, y. You have this rho 1x. Of course, for simplicity, you didn't put y here, but it's kind of implicit. Now, with the definition of rho 1 margin for one data point, we're ready to talk about the definition of rho 1 margin, rho 1. You denote it as rho 1. Not rho 1, sorry, L1 margin. I keep saying rho 1 margin. So the L1 margin rho 1 with respect to a sample. The sample has m examples, and each one is x1, xi, yi, I from 1 to m. So then this definition of L1 margin is just the minimal margin of the points within the sample. So that's rather easy, right? Because you've already know the definition of the L1 margin, which is the rho L1 margin for a data point xy. So then that's going to be like row 1x, right? And then you just take the minimum because you have only m examples. You're just taking the minimal one. Okay, so this seems to be very easy to understand. But one thing I really wanted to mention here is that by this definition, because you are kind of only allowing your label space to be -1 + 1, and this definition would basically ensure that your row 1x, your L1 margin of, with respect to a data point x, will always be within -1 and 1. Okay, this is purely because you have this normalization term here, right? And also one thing important is that this absolute value of row 1x denotes the confidence of g of x, right? As you can see, it's basically saying if row 1x is larger, either is -1 or very close to -1 or very close to 1, it basically means that your classification is very confident, right? So it's talking about the confidence of the strong classifier g of x. Of course, this g of x has been normalized by the coefficient L1 norm of the coefficients. Okay, so that's the second bullet point I wanted to emphasize. And the third one is that when this term is greater than equal to 0, what is this term? When y times g of x, basically, right? Because this alpha transpose hx is nothing but this g of x. So when y multiplied with g of x is greater than 0, as you can see, then row 1 of x is nothing but the absolute value of the inner product divided by the L1 norm of the alpha. This seems to be a rather trivial argument, but why do I care about talking this, right? So you'll see in the next slides, this has a very nice geometric interpretation associated with it. Okay, so that's why I wanted to emphasize this here. And now we're ready to go to the geometric interpretation of the margin. First of all, just to recall, a lot of you already know this, the conjugate norms. So you have P and Q, all greater than 1 or greater than equal to 1. If 1 over P plus 1 over Q is 1, then P norm, Q norm are conjugate, right? For instance, L2 norm's conjugate is itself, and L1's conjugate is L infinity, and so on. Okay, so with this conjugate norm definition, then we're ready to talk about a geometric interpretation of these of the margins. First of all, when again, I'm trying to put the third bullet point of the remark from the next slide here. When the multiplication of y and g of x is greater than equal to 0, row 1 is just this absolute value of the inner product divided by the L1 norm of the coefficient. Now, this row of px, actually, though this is row of 1x, you can imagine row sub px is nothing but replacing the L1 norm here with the LP norm. Okay, so it's essentially the geometric interpretation of this is that it is the LQ distance. Notice that this is normalized with LP norm, but it is the LQ distance of hx to the hyperplane defined by this inner product being 0. Okay, so this is a very important geometric interpretation here. Any questions so far? Of course, if it is row 1x, then this is L infinity distance of hx to the hyperplane alpha transpose hx equals to 0. Okay. Okay, so now as you can see, I'm already putting this question here. What does the hyperplane alpha transpose hx equals to 0 mean in machine learning? What is this hyperplane? Okay, David is saying is decision boundary for the boosted classifier. Any, do people agree with that or disagree with that? People, we're rather quiet today. Agree. Oh, I was looking to see you having thumbs up or something, but yeah, that works if you wanted to type. So yeah, most people agree with that. This is essentially the decision boundary, right? So it's the decision boundary of the strong classifier or the boosted classifier, as David said. So, this is rather interesting, right? This is basically saying that you are now looking, the L1 margin is looking at, so now what is row 1 of X, right? How would you interpret it? Right? If your strong classifier classify X correctly, then this row 1 of X is denoting the distance, the L infinity distance from the point to the decision boundary, right? Yeah. Well, so, the second question is obvious. L1's conjugate is just L infinity, and that's why we're talking about L infinity distance here. Okay. So now with that, sorry, I should have put this first. So the margin loss function is very useful for us to discuss the understanding of the generalization of AdaBoost. So what is a margin loss function? Definition is quite interesting. So for any row greater than 0, it's very important, the strict greater than 0. The row margin loss L row, mapping from real cross real to real plus is defined for all y prime. So y prime are just, you can think of them as 2 labels. Now it's defined as L row y equals to, so you're just using the phi here to denote the margin loss function. It is essentially 0 if rho is smaller than equal to y prime, y multiplied with y prime. And then if y prime is greater than equal to 0 and smaller than equal to rho, is just defined as y minus y prime divided by rho, and then 1 if y prime is smaller than equal to 0. So, what this is really is just looking at the red curve here. I have a plot down here. So you look at the red curve. This is essentially what a margin loss function is. Notice that this x-axis, the horizontal axis, is y prime. Okay, so it's the multiplication of y prime. It's not y or y prime. This is very important here. And then the y-axis, of course, or the vertical axis is just the function value of the margin loss function. Okay, so what this really is saying is, if y prime is smaller than y prime is greater than rho, then it's just 0, right? But if it is greater than 0, smaller than rho, it is just this line here. Yeah, it is just this line here. And if it's smaller, it's just 1, okay? Oh, you can see, actually, this becomes interesting. If you think about the empirical margin loss, so what is the empirical margin loss? We can denote this R hat of H, but now you have a subscript row here. So this denotes the empirical margin loss. It is very important for us to understand this or remember this definition, because we will have to use this a lot in our discussion about generalization ability of neural nets later on. So the empirical margin loss, R hat of row, R hat sub row H, is defined as summation of these margin loss functions. Okay, so what this really says is that, before a loss function, as long as, the y prime is greater than 0, you would let it to be like 0, right? So it's no error. As long as is larger, y prime is smaller than 0, you often just say this is a loss 1. But now this is different. You can see I'm being more strict. I allow it not only to be greater than 0, but greater than some row. The row has to be greater than 0. So it is strictly greater than 0 with some margin. Right? That's exactly how we use margin in English, right? So since this phi row of yi h x I, this function is upper bounded by this function, this step function, which has the step at row. You can see the blue curve I have here. I'm going to erase this so you can see it more clearly. If it's a blue curve, you can see this step function with a step at row is exactly, it is a strict upper bound, but not strict, it's upper bound of this margin loss function. So you can see this empirical margin loss is going to be upper bounded by this step function. Therefore, your empirical margin loss is also going to be upper bounded by this function. So this is very important. Okay. So this is a step function. Sorry, I think you cannot see it very clear. Let me not, do that. Yeah. Okay. So what this is doing is a more strict penalization when you make an error. Actually, even if you're not making an error, but you're not confident enough, then you're still being penalized. Okay. So that's what this step function means. Okay, so let's see, is there any question? In the graph, it seems that row is smaller than 1. Yeah, row should be smaller than 1. Actually, row is bounded between -1 and 1. That's a very good point. Yeah. Okay. All right, so any other questions before we move on? So these definitions are very important. I would, suggest really understanding the geometric interpretation and how this, mathematical form also work. All right. I don't know why I keep doing the reverse order, but so now I'm gonna switch topics. I'm gonna talk about ensemble Rademacher margin bound. So now we have the margin definition. Now, what is so-called ensemble Rademacher margin bound? We have the following theory. It is very closely related to the generalization gap or Rademacher generalization gap theory we had before. But let's see. So this is for H, the family of functions taking value from -1, 1 again, right, with BC dimension D. So this person is just saying H has BC dimension D and takes values from -1, 1. So for any delta greater than 0 with probability 1 minus delta. So it's just with very high probability, the following holds as long as H is within the convex of H, right? So, you can now see why I have this H within convex hull of H. Basically, you're using H to denote some kind of strong classifier, right? Because you can somehow make sure that strong classifier lies in a convex hull of the hypothesis class H, right? Because the base classifiers are drawn from the hypothesis class H. And now, doing a linear combination, Now, if you do some kind of normalization, you can make sure that it's within the convex hull of H, right? And as you recall from AdaBoost algorithm, the linear combination coefficients are usually greater than or equal to 0. So this satisfies this definition of the convex hull. But now, only thing you wanted to mention, or only thing you wanted to take care is that you have to do a normalization, right? Before we didn't do any normalization. So now we'll see how we handle that. So with high probability, this holds. So what is this? It means that the generalization gap, now it is not purely the generalization gap, but it's the gap between the true error and the empirical margin error. Okay, so this is the empirical margin error. As I already talked about in the previous slide, is more strict than the traditional, empirical error in the traditional sense, right? Do people want to go back to that again? So, this is the empirical margin error. It is the summation of the margin loss function, and the margin loss function satisfies this thing here. Okay. So with high probability, this generalization gap is going to be upper bounded by 2 divided by rho, and this is very important here. So it depends on the margin choice, right? If you select rho to be something smaller, what happens? This R hat rho of H is going to be larger or smaller when rho is smaller. Smaller, right? Why? Because just think about the extreme case, rho is 0. Oh, of course, now, let's assume that rho is greater than 0 for now, right? So, here, of course, let's not consider the negative case. So in the extreme case, rho is 0. What is this? This basically means that it is rho, R hat rho of H is just the empirical error, right? But I said the R hat rho of H is more strict than empirical error when rho is greater than 0. So, when rho is smaller, you kind of, the penalization is not so strict. As long as you are a little bit more confident, then, you don't get penalized. But when rho is large, then, rho, R hat of rho H is gonna be much larger, right? Because basically you are penalizing more, even if I'm confident but not very confident, right? So rho smaller, this means this guy is smaller. However, this one of rho, 1 divided by rho, is gonna be larger. Okay, right? Just because it is 1 over rho. So what this is saying is this seems to be a trade-off between these two terms, right? As you can see, the one that I marked was orange. Okay, sorry, erase this. The one I marked was, actually, let me use blue here. So the one I marked was blue versus the one I marked was yellow, right, this term. So you can see seems to be a trade-off between the two in terms of selecting the rho, because when rho is smaller, the first term is smaller and the second term is larger. But when rho is larger, the first term is larger, but the second term is smaller, right? So you essentially wanted to minimize this upper bound so that the true error will be minimized. So that's why you have this subtle trade-off between the selection of the rho. Okay, is this clear? Any questions? Also, if you look at the term, so I don't plan to prove the theorem here, since we don't have enough time in class. I highly suggest everyone go back and read the textbook. But you know, if you look at the form of this upper bound, what does this remind you? It's very similar to this VC dimension generalization bound you see before, right? It's very similar. Only difference is now you have replaced this empirical error with this margin error, empirical margin error, and you also have the term that's dependent on what to overrule here. Okay. All right. So the first remark is that for AdaBoost, the bound applies to the function. Remember? So it has to be applied to the function with this normalization, right? It is very important to have this normalization. Otherwise, it won't be in the convex hull of H. Okay, so that's the first very important point. Then the second point is it has to be independent of, it is actually independent of H. Oh, sorry, it's independent of T. So what does this mean? What does the independence of T mean? Do we have another question? Is this related to the independence of T here? The summation is over I, and inside the summation, the subscripts are T. Oh, yeah, that's actually a very good point. So yeah, so that's not, yeah, so this is actually wrong. So we should, this is a typo here. We should actually say, this is the T. Yeah, very good point. Okay. Yeah, exactly. So the implication of this independence of T is just that the generalization bound holds regardless how many base classifiers you use. Exactly. Yeah, and also Jonathan said that we don't overfit as we increase T. But there is a caveat here. What is the caveat? As I said here, you have the denominator that normalize the L1 norm of the alpha. Remember, we don't have that in boosting, right? So let's see why and how we can come up a solution. Okay, so in order to show how AdaBoost is resistant to overfitting, we're going to do the following. We're first going to show the ensemble VC dimension margin bound, which is something like this, right? We're just repeating the term here, right? So we've already seen it from the previous slide. So this guarantees an effect of generalization if margin loss is small for a relatively large row. Okay. Also, we're going to have an argument about the margin distribution. I don't have, I'm going to prove it later on, but I'm gonna first give you the result. So the margin distribution, we wanted to see that for any row, as long as it's greater than 0, the so-called empirical probability that the margin being smaller than equal to rho. So what does this mean? This means that if you are taking, if you're looking at all the examples in your training sample, in a sample, then for what is the, I shouldn't say probability, but I should say what's the fraction of the training examples such that the L1 row, the L1 margin is smaller than equal to row. Does that make sense? Are people discussing something else? So is there anything I need to discuss? Do you want to speak up? Not sure what the discussion means. Yeah, I'm not sure. If you don't want to discuss now, you feel free to discuss in the chat. So let's continue. So the margin distribution here, this distribution, I don't want to call it distribution. I really wanted to say this is the fraction of training examples such that, that has a more L1 margin smaller than equal to row. Okay, that's simply that. And if you see, it can be expanded as the summation of the summation of this indicator function over all training examples divided by m. What is this indicator function? This indicator function just says that yi(hxi) minus alpha one norm, L1 norm of the alpha multiplied with rows being smaller than equal to 0. So this basically means that the L1 margin is smaller than equal to row. Okay. So with this indicator function, you just calculate the fraction of that, a fraction of the examples that satisfy this event. So we are going to prove, you don't know why I have this yet, but we'll see that in a minute. So we're going to prove that this is upper bounded by 2 to the power t and product of the square root of epsilon t to the power 1 minus rho and multiply with 1 minus epsilon t power 1 plus rho. Okay, so this is very important. And essentially with that, we'll see if for any t, the rho is being smaller than equal to half minus epsilon t, then the empiric, so the I would say margin distribution or the proportion of examples such that the L1 margin being smaller or equal to rho is going to be upper bounded by this term here. Okay. So because we know that it's upper bounded by this, then if rho is being smaller than equal to half minus epsilon t, then you have that. So as long as you have that, of course, we're going to prove this. You don't know the proof of this yet. And this, sorry, how do I write this? Yeah, so this one we will prove later. Okay, so we know that for rho smaller than gamma, this term, this 1 minus 2 gamma to the power 1, minus rho, multiplied with 1 plus 2 gamma power 1 plus rho is smaller than 1. This is just by math, we know that. Then therefore, this entire upper bound decreases with t. Right? Because it is just this thing with a power t to the t half of t, right? So with that, then the third step we are going to say is that therefore, the first term, the blue term, essentially requires gamma being greater than rho, right? Because we know that as long as gamma greater than rho, this term will decrease with t. So we will make sure that this term is smaller than something, is very small or very close to 0 as t increases, right? Then also, you want to make sure that the second term, the red term, also goes to 0. How can you guarantee that? You can actually, as long as rho is greater than some order of 1 over square root of m, okay? As long as this satisfies, then the gamma is gonna be greater than equal to some order of 1 over square root of m. So what this means is that as long as the gamma is greater than this term, you can guarantee that AdaBoost is resistant to overfitting. With one thing that is still unclear, which is how do we prove this margin distribution? So I'm gonna pause a second. I'm gonna see whether people have confusions about this slide. This is a very important slide. It is the overall idea of how we can show AdaBoost is resistant to overfitting. It's also very important to notice that here we're using the ensemble VC dimension margin bound. We are, deliberately putting this term, the blue one, the margin loss, we're deliberately using f of x divided by L1 norm of alpha. It's very important to notice that, right? This guarantees that the strong classifier will be in a BC, it will be in a convex hull. However, if you do that, then this basically changes this red term in the second term here, right? Because you can see it depends on, we didn't see the proof of this, but if you see the proof, you will see this will give you this term, and this term depends on the rho, but not depend on the alpha, which is very interesting to see. Okay, so the first step is just the ensemble VC dimension margin bound. As long as you have that, if you wanted to prove that AdaBoost is resistant to overfitting, you basically wanted to say that the upper bound is actually could be made very small, right? How do you do that? You wanted to first making sure that the blue term is very small. How do you do that? Basically, the second step, margin distribution. You say that, okay, this term is actually upper bounded by this quantity, which is essentially something to the power t over 2. So if this something is smaller than 1, then as t goes to infinity or goes to a very large number, this term will go to a very small value. So it's very important to making sure that the base is actually smaller than 1. Okay. Now, the second term, the second, that's not enough yet, right? You want to make sure the second term is also smaller, or is a very small value. So it essentially requires the rho to be greater than some order of 1 over square root of m. So if rho is smaller, if you, can only make rho to be smaller, then you would have to increase the number of training examples m in your sample. So it's not like it is always resistant to overfitting, even if you have a very small number of examples. You still have to have enough number of examples. At least it's going to be greater than, some function related to rho, right? Rho has to be greater than order of 1 divided by square root m. Okay, so let me see where, I think there's a lot of discussion now, but do people want to speak up, or should I just read the chat? What should we do? Okay, so I'm gonna pause for maybe 2 minutes or 3 minutes, and people can feel free to speak up or have a discussion. Any questions? Okay, if there's no more questions, I'm gonna proceed to the proof of the to the second step, this margin distribution. So we wanted to prove that this fraction of so this is very important. I'm using probability to the with a hat. So this just means the empirical one. So it's a fraction of training examples such that the L1 margin is smaller than equal to rho. Okay, it is not the true distribution. So you wanted to prove that this empirical distribution of margin being smaller than equal to rho is upper bounded by this term. How do you do that? So first, you recall the definition of the empirical distribution at time t+1. It is nothing but something related to, okay, I think I forgot the alpha here. Yeah, I think
Isn't alpha part of the f of xi?
Yeah, so I think here also I forgot the alpha here, right? Because the the distribution is related to exponential of the minus alpha. Yeah. Well. Yeah, the thing is, okay, yeah, so I see. Okay, I'm gonna erase this. So the thing is, actually f is already included. Do you see? So, f is already, so that's why we don't have a typo here. What is f of xi? F of xi is already summation of the alpha t of ht of xi, right? Actually, let me say s. Maybe this is better because I'm gonna use t as my ending of the, okay, give me 1 second. So let me write this down. Don't have a confusion here. So you can see summation, the f of x is the ensemble classifier. Let me use s to denote the base classifier index, and we are summing over until t because I'm at round t now. So I'm doing that. Alpha t of xi. Actually, let me just use alpha t. I believe that's what we were using before. So alpha t multiply with ht. Oh, not t, right? S. Alpha s hs of xi, right? Summation s from 1 to t. So if that's the case, then you can see that's why this d of t plus 1i is exponential of minus yi f of xi. You don't have the alpha here, and then divided by m and product of the zt. Right? Any questions? Do you see why? So before it should be I have no space. Yeah, this is annoying. I cannot write here. I'm gonna let me erase this. Yeah, so this is let me see, multiply with exponential minus yi. Right? So before, this was my definition of the dt plus 1i. Now I'm just replacing this with my f of xi, which is the current strong classifier. Okay? Is this clear? Okay, wonderful. Now we're ready to proceed. So we know that this quantity this is the the average of these summation of the indicator function, indicating that this L1 margin of the F, L1 margin of the X is gonna be smaller than equal to rho. Okay, so we know that this step function is upper bounded by the exponential function, right? This is a step function that is upper bounded by this exponential function. Do you still remember how? We did this when we proved the empirical error of AdaBoost, right? We said the step function is always upper bounded by an exponential function. So error step, 0, 1 error is upper bounded by the exponential. So now what you do is essentially you are just rearranging it, right? So this term becomes this term by simply rearranging things, okay? Do you see that? Any questions? Right, you have that. Therefore, oh, shit. Yeah, you have this term here. So you're just rearranging things and you get this term, okay? Now, of course, because you can just take this out. The only thing that's dependent on I is just this term. So you take it out and the summation is just 1. And you're also canceling out this m here. So overall, it becomes just the exponential of this alpha L1 norm multiplied with rho and product of the ZT. Okay, so also you know that alpha t is chosen to be half of logarithm 1 minus epsilon t divided by epsilon t, and zt is chosen to be 2 multiplied with epsilon t 1 minus epsilon t half to power half. Then you know that this holds, right? Just by replacing the alpha and the z. Okay, so overall you've achieved this margin distribution proof. So let's go back to the slide again. So you've proved that this empirical distribution of smaller, empirical probability of smaller than the rho, margin smaller than rho, is upper bounded by this term. Okay. All right. I think it's relatively easy to understand. So I'm gonna proceed, but feel free to interrupt me if you have more questions. Okay. So now this is rather interesting. We will see.
Hello, how do you choose? Sorry, how do you choose alpha t based on epsilon t?
This is by definition. Remember the algorithm. We've chosen alpha to be in your AdaBoost pseudocode, chosen alpha t to be this way, half of logarithm 1 minus epsilon t divided by epsilon t.
Okay, thank you.
No problem. Other questions? Okay, so I'm gonna introduce some very basic game theory notations, but the purpose of that is really to show that there is a very interesting game theoretical view of AdaBoost, and we'll see essentially what that means. So let's just talk about the zero-sum games. A lot of you already know what it is. So the definition is quite simple. You have a payoff matrix, right? The matrix is m by n, and so that means you have m possible actions for row player, and if a column player also has n possible actions. So the payoff matrix basically is like denoting the payoff for row player, or you can think of the loss for column player, right? So here is an example where you have rock, paper, scissors between two players, row and column. So the player row is going to give a rock, and then the column player also give a rock, then it's gonna be 0. So nobody wins, right? But if the row player is rock, but the column is paper, then the row lose. It get a -1 payoff, whereas the column get a -1 loss, which means it's a 1 payoff, right? So this is just a definition of the payoff matrix. Now with that, actually, von Neumann actually had this very interesting minimax theorem based on a mixed strategy. What is the mixed strategy? It just means that the player row selects a distribution over the rows rather than a hard strategy, right? Either I do rock, paper, or scissors. This is a hard strategy. But what I can really do is I can select a distribution. I'm going to say with 20% probability, rock, 30% probability cedar, and so on, right? So the player column also a distribution Q over columns. So then the expected payoff for row is going to be the expectation of the Mij, which is the summation of Pi multiplied with Mij and Qj. Okay, so it is nothing but the P transpose MQ, right? So that's the expectation. Very simple, nothing game theoretical yet. But the von Neumann theorem, minimax theorem, says that the max mean of this expected payoff is gonna be the mean max of this expected payoff. Okay, so no matter whether you do the minimization first or maximization first, it is equivalent. Also, the equivalent form is that if you have a minimization of the J, okay, so what is the J? J just means I am trying to minimize the payoff through, choosing one strategy for the column player. Now, so then if I do that, and also on top of that, I do a maximization of the P, so the row player choose a distribution that maximizes the expected payoff, then it's equivalent as the row player first choose a fixed strategy that maximizes the payoff. Then the column player do a minimization, find a distribution Q over which it minimizes the payoff, expected payoff. Okay, so this is rather interesting. Of course, apparently we don't have time to review these, but let's see, how does this imply that? How does it affect our understanding of the AdaBoost? So AdaBoost can be thought of as a game between player A and player B. What is the player A doing? The player A is essentially selecting points, xi, okay? So it is selecting xi from this training sample. Okay, so I could be from 1 to m. And now the player B is going to select base learners. So the base learners is going to, give you HT, and the T is chosen from, 1 to T, capital T. So what is the payoff function, payoff matrix? The payoff matrix is essentially the ith row and the tth column is just yi multiplied with ht of xi. Okay, so what does this mean? This means that your row player, which is player A, and a column player, which is player B. No, so what this means is that the payoff function just becomes, each element becomes the ground truth label for the choice of the point, as well as the prediction of the base learner. So if the base learner actually predicts the same as the ground truth, then the payoff is gonna be 1. Otherwise, it's gonna be -1. Okay, so now very interestingly is that you will try to so von Neumann theorem said that if you have a finite H, then what happens is that this 2 times the gamma star, gamma is actually something you find from AdaBoost, right? So 2 times gamma star is going to be the minimum of the distribution, the empirical distribution, how you select points. So here you can see the D is not like selecting one of the points, but a distribution over the points corresponding to this thing here. This is a mixed strategy, okay? And also here, the Q is the mixed strategy. So this D is just corresponding to how much you weight these empirical examples. Now you can see why we're doing AdaBoost this way. It's basically motivated from this von Neumann theorem. We have a mixed strategy. You're not choosing one example at all. You're choosing a mixed distribution over these examples. So you have the D, which corresponding to the D hat at T, right? So what we were saying, the empirical distribution of how much weight you put into each example. Now you're choosing a maximization. Oh, this is now not a mixed strategy. This is just choosing one, right? Choosing one base classifier. So, this is the mini max of this payoff. This payoff is just, summation of the DI, YI, HXI, right? So, the distribution is trying to minimize the payoff, whereas the base learner is trying to maximize the payoff. Okay. Now, von Neumann theorem says that this is equivalent as doing the opposite, right? You first minimize over these training examples. Then on top of that, you are doing a maximization. So this maximization is not purely just a pure strategy of choosing which classifier. It is the distribution of how you choose these classifiers. So that's why it's called alpha. Right? And now you can see why we are normalizing, these coefficients. The strong classifier was the L1 norm of the alpha. We want it to be a distribution. We want it to be a probability vector. That's why we're doing this normalization with the the L1 norm of the alpha. Okay, so now you can think about alpha as like a distribution. Now, so based on von Neumann theorem, these are equivalent. And if you denote this as rho star, this is going to be the optimal answer for this minimax problem. And it turns out is exactly 2 times the gamma star. Okay, does this make sense? So basically, what this tells us is that this weak learning condition is a non-zero margin, basically, right? So if you satisfy this weak learning condition, you have a non-zero margin. And essentially, AdaBoost is a suboptimal search of a corresponding distribution alpha that actually only achieve half of the maximum margin. It is not an optimal solution based on this theorem. Okay. Actually, they can use some linear program to do that. We'll see very briefly afterwards. But more importantly, as I hinted at the beginning of the lecture today, this weak learning condition is actually rather strong. It says that the data have to be linearly separable with a margin 2 multiplied with gamma star greater than 0. So basically, your data itself is not, it's separable, it's linearly separable. Okay, so now you wonder, right? AdaBoost seems to be suboptimal, although it's quite strong already, but it's suboptimal. So can you somehow achieve the rho star? And so, of course, the answer is yes, you can maximize the rho. And, basically you can just directly solve this optimization problem. If you go back, this rho is nothing but here, the maximization alpha minimization of the points of this yi of the strong classifier normalized version. So if you just do that, you will see you can directly maximize the margin. And this is equivalent to a convex optimization LP problem. Okay, so it is just maximizing the rho subject to that the yi multiplied with the inner product is greater than equal to rho. And also the L1 norm of alpha is 1. Okay, so I'm not going to go into too much details of this, but this is just to give you an idea that although AdaBoost is very powerful, it is not the optimal solution in terms of the margin. The margin could be solved better in a more optimal sense using this linear program, convex optimization linear program. Okay, any other questions? So I'm gonna wrap up this, AdaBoost using some explanations of the advantages of that and weaknesses of that. So, we've learned about AdaBoost. Now let's reflect. What are the advantages of AdaBoost? First of all, the implementation seems to be rather straightforward, right? You have a weak classifier. No matter how you get that weak classifier, you somehow get it. And then you just, somehow the next round, you kind of reweight the training examples with different weights, depending on whether you make whether you make a mistake on these examples. So if you make a mistake, you make that example more important. If not, you kind of make that example less important. Now with that, you just get a new classifier. You just train the new classifier, a new base classifier on the weighted examples. And do that again and again. You use like a linear combination to get the final result. Okay, so it's rather simple and it's also kind of efficient. Basically, if you have very simple base classifiers, the complexity is just m multiplied with nt. Okay, so also, if your n and t are not very large, the algorithm is just quite fast. But more importantly is the theoretical guarantees, right? So the theoretical guarantee that the empirical error converges to 0 with exponential rate also is resistant to overfitting as long as the rho is greater than 0 and somehow as long as the rho and the gamma satisfy some condition, right? So of course, there are other questions like AdaBoost is not designed to maximize the margin. It is actually a suboptimal solution. So there are some other versions of the AdaBoost. Unfortunately, we don't have time to cover them. But more importantly, I wanted to talk about the weakness of AdaBoost. First of all, we need to determine t, right? We cannot just let t to be a huge number. It is going to be computationally expensive, and it's just not feasible. Sometimes you just cannot come up with such base classifiers, so many base classifiers. So you need to determine t, basically the roundup boosting. And people might come up with some stopping criteria, which is not very clear here. Also, you need to determine the base classifiers or the base learners. However, as if you notice that if you find a base classifier that has a very, very small gamma, then or gamma t for that base classifier t, then you still have the risk of overfitting, right? Because in order for it to be resistant to overfitting, you have to satisfy some condition, and the condition requires the gamma to be large enough, right? So therefore, you still have the risk of overfitting if you couldn't find good quality gammas or good quality base classifiers. Of course, as Mario Mori also put on his slides, that if you have noise, sometimes it could severely damage the accuracy of the AdaBoost algorithm. Essentially, people have done a lot of improvement in, based on AdaBoost, regularized version, or like deep AdaBoost, so deep boost or something like that. So we don't have time to cover them, but yeah, so those basically are like improved versions of AdaBoost. Okay, so I don't think we have time to cover the generalization of deep neural nets as I wish we would at the beginning, which is fine. So this is great. So we will focusing on the generalization of deep neural networks. And yeah, I believe TAs have put the reading requirements, a few papers to read. So please make sure you read those papers before coming to class. I won't be giving a very detailed review of the paper, but I will extract more important points, and hopefully we can have a discussion over these points, right? More like, asking questions, how to understand these points, how does that relate to our theory we learned in classical learning theory, and so on. And as I promised, I will also cover the robustness of deep neural networks, but I think we will spend 1 or 2, even 3 lectures on the generalization of deep neural nets. So I'll give you the reading later on when we're towards finishing the generalization of deep neural nets. Okay, so any other questions? If not, I think we will end today's lecture here. Thanks, everyone.
Thank you.
Thank you.
Thank you.